All right, so yesterday we went through kind of half the problem. And just as a reminder, this was, or this is, what I should say, this is the scenario that we're going to have for the assessment. So there's going to be a ball that's going to be sliding down the ramp. It's not rolling. It's going to slide down the ramp with no friction, no air resistance, and there's going to be 3 different states. So this animation, I designed it so it would loop, but we're only going to focus on half of this animation. So the time where it is at the top of the ramp, and then when it gets down to about right there. So this is where the problem would end. So there's 3 different states. State 1 is at the top of the ramp. State 2 is at the bottom of the ramp. State 3 is when the spring is fully compressed. So what we covered yesterday was at state 1, we have only gravitational potential energy. At state 2, we only have kinetic energy. At state 3, we only have elastic potential energy. Okay. And what I did was, in my lectures, in my 3rd and 4th block, I actually typed the questions up so it's easier to read. And you can look at those videos. They're on my channel. Okay, so that's basically what we covered yesterday. So what I want to do is I want to figure out what is the velocity at state 2 and what is the kinetic or the spring constant at state 3. So I want to know how strong is that spring. Make sense? So that's my objective. And we're going to figure that out using these knowns. So I'm going to give you the mass, I give you the acceleration due to gravity, I give you the height of the object, like when it's at state 1, so h1, and then I'm going to give you the displacement of the spring, so how much it's being compressed. And by using those knowns, we're going to figure out how fast it's going when it's at state 2, and then we're going to figure out how strong is the spring. That's our objective for today. Any questions so far? All right. So, the conservation of energy states that all of the energy throughout the entire process is conserved, assuming that there's no thermal energy or energy loss to air resistance or anything like that. In an ideal situation, all of the energy that I start with will equal the same throughout the entire process. Okay, so that's why when you see this video or this little animation, it's going back and forth. Okay, and it's not slowing down. If I was losing energy, it would not travel as far up. So in other words, it would hit the spring, and then it would end up stopping like right there, and then it'll come back down if we had friction or air resistance. But we're dealing with an ideal situation, so I know that all the energy that I start with remains the same no matter where I am in the process. That's what the conservation of energy means. So, in order to figure out the type of energy that's present at each state, we're going to look at what we did yesterday. So the energy at state 1 was gravitational. So that's going to be U grav. Cool. Right there. And then the amount of energy at state 2, the total amount of energy, sorry, so state 1, state 2, state 3, the total amount of energy at state 1, total amount of energy at state 2, and so on. So we have kinetic, and then we have U elastic. So state 1, state 2, state 3. They're all equal to each other. Make sense? Then what I did was I took what U grav is, so the equation for gravitational potential, U grav, is equal to m times g times h. All right, that's the equation for U grav. So what I've done is below this, I've plugged in, or I've substituted in what it is equal to. So U grav is equal to that. Kinetic energy is equal to this. elastic is equal to that. Make sense? All right. So what I'm going to do is the variables that I want to solve for, I'm going to write in red. So I'm solving for V2. Now the subscript 2 just represents that it's at state 2. And then my spring constant, that's representing how strong the spring is. So those are the two things that I'm solving for. Now, the reason, if I look at this, there's no red variable in here. So that should mean that I know those variables. So let's check our knowns. So M, G, and H. So here I've got H1. That's just representing the height at state 1. So technically I could put a 1 right there. Make sense? All right. So since I know everything in this section, I could technically get an answer. I could get a number. Now this is the symbol for a number, not a hashtag. So if I get a number, that means that I can solve for this side. And I know that that must equal this number, because of the conservation of energy. So what we can do is I can take this side that I can solve for, and I can set it equal to this side, and then solve for that one unknown. And that would be solving for V2. And then I can set it equal to this one, and then solve for that. So that's our game plan. Now, you will not have to do this. So for the assessment, all you would need is the final equation, and I will box it and star it and make sure that you guys understand which one to use. But you don't have to do the algebra. All right, I'm showing you guys where these equations come from. So when you go back and you're like, wait, where did this equation, like why am I using this equation? You can go back and reference this video. Cool. All right, so let's go ahead and solve for V2. So like I mentioned before, this is state 1. I don't know what that was. This is state 1, and then this is state 2. So what I'm going to do is I'm going to set state 1 equal to state 2, and I want to plug in. So state 1 equals state 2. And then I'm going to skip a couple steps. I'm just going to plug in what they're equal to. So M times G times H, 1. And then 1/2 times the mass times the velocity squared. And since I'm solving for the velocity, that's going to be velocity at state 2. So this is my equation. I have one equation and one unknown. So what I want to do is I want to solve for V2. I want to get that by itself. So how do I do that? I need to first get rid of this 1/2, so I multiply by 2. 2 times 1/2 just goes to 1. So this cancels out. And if I do it on the right side, I do it here on the left side. Now I have mass times velocity 2 squared. Divide by m. Divide by m. So it cancels out over here. And it actually cancels out over here too. And I'm going to rewrite it so it's a little bit cleaner. So on the left side, I have 2 times gravity times h1. And that's equal to my v2 squared. So in order to get rid of a square, I square root. So the square root and the square cancel out. And if I do it on the right side, I must do it over here on the left side. So now the final equation for V2 is going to be 2 times G times H1 all underneath the square root. Cool. So this is one that you should write down because you can use a formula sheet on your assessment. Any questions? Okay. So just as a side note, I'm not even touching what the values are for my variables yet. Okay. What I'm going to do is I'm going to solve for my spring constant next, and then I'm going to show you guys how to plug these things into Desmos. Desmos is a little tricky, but I want to show you guys a cool little trick that basically guarantees that if your equation visibly looks exactly like this, then you're going to be guaranteed to get the correct answer, as long as you round properly. Okay, I'm going to show you a foolproof way how to do this, but I'm going to do that in just a minute. All right, so that's the final equation for V2. So now I want to solve for the spring constant. Now the spring constant is located here in state 3, and technically I could set it equal to state 2, but I am solving for V2. I am not given V2. So because I'm solving for it, there's going to end up being some sort of rounding error. Chances of it happening the chances of me getting a perfect whole number is going to be pretty difficult, especially since we're doing a square root. So if I take this, remember, I can only plug in values that I'm given. Since there is an unknown that is not located in my knowns box, it is not here, I cannot plug anything in because that will introduce round-off error or some sort of, I forget the term. It's early in the morning. Not uncertainty, but margin of error. You can get a more accurate answer if you use one equation and only having one unknown. Make sense? So this is going to look very similar to the one previously. So we're going to have state 1 equals state 3. State 1 was mass times gravity times h1. And then for state 3, we have the elastic potential energy. And then delta x squared. Has Jackson come back in? Did Jackson show up? Yes, he did. Okay. Did Kimon show up? No. Trevor and Wendy, no. Okay. Remember, guys, to let me know when you come in late. I don't want to mark you absent when you actually are here. All right. So the variable that I'm solving for is the spring constant. So this one's actually going to be a little bit easier to solve for. Yeah, I got you, Jackson. All right. So since k is the one that I'm solving for, I need to get my 1/2 over to the other side, and I need to get this delta x squared over to the other side. Now remember, the delta x squared is just telling me how much my spring is being compressed or stretched from its rest length. So in order to get rid of the 1/2, multiply by 2. So that cancels out there. And since I did it on the right, I did it over here on the left. And then since I've got k times delta x squared, I can just divide by delta x squared. So this will cancel. Divide by delta x squared. And this one's a little bit easier, like I said. So I get my spring constant, a lowercase k. This is not equal to this. These are not equal to each other. This is the spring constant. This is kinetic energy. Do not get those mixed up. All right, so my spring constant is equal to 2 times the mass times the acceleration due to gravity times h1 times delta x squared. So this equation here is one you should write down. All right, so while you guys are copying these two equations, hopefully you can see them. And what I'll do is actually put this over here so I can zoom in a little bit. Okay. All right, so while you're writing that down, I'm going to get Desmos set up. Okay, so the first thing that we're going to do is we're going to set up this equation into Desmos. So one of the cool features about Desmos is I can actually plug in variables, and then I can use Desmos to change the value of that variable and then alter my answer. So watch this. If I switch over to Desmos, I want to get my equation to look exactly like this. So 2 times g times h, and I'm just going to use h just to plug it in, and then all of that underneath the radical. So watch. I'm going to go down here to the keyboard and put in a radical. 2 times g times h. And just to make sure, I look at that. This should visibly look exactly like what I've got written here, except for the subscript 1. And if it is, what you can do is I can click all where it says add slider. And what this does is this is modifying the value of g. This is modifying the value of h. Now, if I go back and look at my knowns, g is 10. So what I'm going to do is I'm going to select this. I'm going to type 10. And then h is going to be 100. So h is 100. So here I'm going to do 100. And would you look at that? It automatically gives me my answer. Now, if you do this and you're not seeing this answer box, chances are that you have put a comma in your problem. So if instead of 100, I had 1,000, right? But then instead of doing 1000, you did 1 comma 000. Notice how there's no answer left, or there's no answer shown. That's because Desmos doesn't like commas. Get rid of the comma, and there's your answer. So the answer about how fast the object is going at state 2 is 44.72. So the velocity at state 2 is 44.72 meters per second. Now, I want to briefly give you guys a refresher on how to round. It's kind of surprising about how many people, for some reason, don't remember how to round properly. So what I'm going to do is I'm going to do that really quick. So if I say round to 1 decimal, round to 1 decimal point, what I mean is 1 space after the decimal point, that's the value that I'm looking to modify. Am I going to round up and add 1 to it, or am I going to round down and keep it the same? And in order to determine that, I look at this value and then the one right next to it. If it is a 5 or above, I'm going to round up So that 7 now becomes an 8. But if it is a 4 or below, I'm going to round down and keep it a 7. So if I'm rounding to 1 decimal point, the answer I should get is 44.7, because this is a 2 that is below 4, so I'm going to round down. So this would be meters over seconds, velocity at state 2, and that is my final answer for the velocity at state 2. Now, all the stuff that we've done up to this point, you don't have to do on the assessment. All you need to know is this equation. You need to write down what you know and what you need to find. You just plug in your knowns into Desmos, get your answer, and round properly, and then you're done. That's all it is for the assessment. So I've done half the assessment right here in, if I wasn't talking, less than a minute. Cool. So, with this one's a little, oh, never mind, you can't see it. When I'm trying to solve for the spring constant, so let me show you how I do this in Desmos. So I'm going to switch over. And this is where it gets a little weird. So watch what happens. If I do 2 times m times g times h, so 2 times m times g times h, and I want all of that on top of delta x squared. So if I do a division symbol, if I try to divide, watch what happens in Desmos. If I hit divide, it only goes under the h. Now technically this is still mathematically correct, but we want to make sure that it looks exactly like it, just to guarantee that the order of operations is done properly. So in order to get it from doing the last variable and dividing under it, what I can do is I can do a closed parentheses, and then you'll notice that it automatically puts an open parentheses at the beginning. And then I'm going to go back to the end. Then when I do divide, everything's on top. And then I'm going to do open parentheses. I'm going to do x. It doesn't matter about putting the delta, because this is just a very simple formula. And then I'm going to square that. So when I look back at my equation, 2 times m times g times h on the top. 2 times m times g times h. On the bottom, I have x squared. And here it's delta x squared, but again, the delta is more for a visual representation. Okay. So now, wait, why is the x not there? Oh, that's interesting. So apparently you can't use the letter x. Because it's a graph. So we'll just say d for distance, displacement. Okay. So if you guys are following along, that's why it didn't pop up, because it's trying to graph it, and x is the variable that they use for that. So if that ever happens, if I've got letters up here and it doesn't pop up here, just try a different letter to represent that. So I'm going to hit all, and then all I have to do is plug in the values. So mass is 50. So I'll put in 50 right here for mass. Gravity is 10. Height is 100. So I did 100 right there. And then my displacement of the spring is 0.75. So 0.75. And here's my answer. So I really wish that they would put commas in there so it's easy to read. So this apparently is a very, very strong spring. So my spring constant is equal to 177,777.77 newtons over meters. So if I wanted to stretch this spring a distance of 1 meter, I would have to apply 177,777.777778 newtons in order to stretch it 1 meter. So if I say to round to 2 decimals, it's going to be the same process as before. This is 77. That goes on forever. So I look at my second decimal spot. That's going to be this one right here. I look at the location right next to it. So that's going to be a 7. That's above 5. So that means that this one is going to be increased by a value of 1. So my final answer for my spring constant is be 177,777.78 newtons over meters. Cool. Does anybody have any other questions? Is anybody confused? Comments? Pretty straightforward, right? Now again, the steps that I took today is giving you the background on how I developed the algebraic expressions here. I was showing you how I got this and how I got this one. So like I mentioned before, you don't have to do this algebra. If I give you a problem where it looks like this, I give you the mass, I give you acceleration due to gravity, I give you the height, and I give you how much the spring has been compressed, and I ask you to find the velocity at state 2 and the spring constant at state 3. The only 2 equations you need is this guy and that guy. Okay? And then all you have to do is plug it in, and then you're good to go. All right? I'm going to go ahead